Hey, we've got Ryan. Let's adjust this a little bit. That's pretty good. We've got Ryan on board. Let's see who else we've got. We have Ashley. We've got a good class already. We've got Ryan and Ashley. All right. Yeah, we're 4 minutes early. Did you guys have any questions for me? Well, let me write down the kind of stuff we're going to study today. Let's see. Yeah, this is the 30th of September. And we are going to study the work energy theorem. And we're going to study power and efficiency. And conservation. Maybe a little bit ambitious there, but we'll see what we can do. Well, we got a couple of minutes before class starts, and we just have two students right now. Ryan, Ashley, did you have any questions for me?
Not at the moment.
That's fine.
Me either.
That's just fine. Well, what about Ryan? Ryan, do you have any questions for me?
Oh, I'm good.
Okay. Well, if you're happy, I'm happy. Now, I think I've talked about this before, but I want to show you where it comes from. They actually derive it on page 184. I call this the work energy theorem. That's what I call it. It's the work energy theorem. This is the way I write it. Now, the way the book writes is weird. The way the book writes it is like this. You'll see that in the book on page 184. But it says the same thing. This is their secret symbol for work. They use a U. Don't you like W better for work than U? I do. I like W better for work. And kinetic energy, I like KE better than T. See, T1 is the initial and T2 is the final. If you move that initial over here and subtracted it, you'd have the change in kinetic energy. So it says the same thing. It's just that they're being weird is all. I think what it is they don't want too many engineer graduates out there. So they're just weeding you guys out, which is kind of crazy because I think China produces 5 times more engineers than we do. And they're good too. They're not bad. So I think we need more engineers, more excellent engineers, and that's what I want you guys to be. Or whatever, scientists or whatever you're going to be, lawyers or whatever. But if you wanted to show where that came from, here's what they do. They'll take work, and I'm going to use the symbol W. And you know it's really a definition. In case you're dealing with vectors, it's a dot product. You'll find that's a definition of what work is. It's a force times distance. But see, if you just take the tangential component of your force, it's always in the direction of your distance that you travel, because that's what the tangential direction means. It means the tangential direction is in the direction of your path or velocity, either one. Hopefully your velocity is in the direction of your path. So you don't need vectors there if you have that. Now here's the thing. If you wanted the total work, we'll put a sigma sign here, then you would have to take the total of all the forces, but you only need the total. Oops, not much room there. Let me scoot that over. You don't need the forces, the components that are not in the tangential direction. All you need is the sum of the tangential components, because the other, the components in the normal direction, they don't do any work. See, the normal direction is always perpendicular to the path, and you're not doing any work. You got to go. To do work, you have to have a component along the path. Okay. And we have a little equation that goes like this. I know you've seen it before. Let me call on one of my excellent students and see if they remember the name of that equation there. Oh, look at all the other wonderful students that have showed up. We've got Mark and William and Stuart and Nicholas. Let me pick on Nicholas. Nicholas, unmute and say hi.
Hello.
Hey, hello. Hey, Nicholas, this is an important equation and it's got a name. What's the name of it?
And it's just called Newton's second law.
Yes. Yes, Nicholas knows what that is. It's Newton's second law. That's what it is. Good going. So here, let's just stick it in here. See, we're adding up all the works done on a body. And we're just following along here. We use Newton's second law. We're here. We have another equation that we learned. It's a kinematic equation. Now, we learned that in one dimension. But see, if you're just going in the tangential direction, you are in one dimension. Because this tangential acceleration has to be in the same direction as your displacement along your path. You guys remember this equation. In fact, I derived that long ago. What is this, September? I derived that equation in August for you guys. I tell you where it came from. It came from the definition. You might not remember me doing it, but it came from the definition of acceleration. We were just in one dimension, which we are now. And I started with that and I came up with that. Go back and look at your notes. Okay, now we're going to do a little algebra here. You see that ATDS right there? Well, there's an ATDS, isn't there? So you could write this as the sum of m v dv. Now, if you're integrating with respect to velocity, you'd need to have a v1 and a v2 right there. Okay, we're almost done. Let me erase this here. Well, I'll leave it there for a minute. Now this here, we're going to pull the mass out because it's constant. And here's what we've got now. We're almost done. The sum of all the works done is equal to the integral of, or mass times the integral of v dv. When you will go from v1 to v2. And you guys know how to do that. That's v squared over 2 from v1 to v2. You know what that is? That's 1/2 mv2 squared minus 1/2 mv1 squared. And now you recognize that. You know what that is. That's what we call kinetic energy. So what you got here is the change in kinetic energy. We started with the sum of all the works done on a body, and it's equal to the change in kinetic energy of the body. They call this the work energy theorem. That's the name of it. Very powerful. It's the second most important equation in our course. This right here is the most important equation. Of course, that's just the component form of it. You can write that in various ways depending on what component you want. Like you could have x's here and put an x there, or that could be a y, or it could be an n, or the r. You could have the radial component, that would have to be an r, or theta, that could be the transverse component, but that's Newton's second law. That's numero uno. That's the most important equation in our course, Newton's second law. And I think it was Nicholas that knew that. Now, the second most important equation in our course is this one here. Great. So we did that. I wonder if we should work a problem or if we should maybe go on and do some more theory. Let's do a little bit more theory while we're there. Yeah, maybe we'll do some more theory. Do you have any? Yeah, we're going to talk about power and efficiency now, but do you have any questions so far? Okay. Well, let's talk about power and efficiency now. Now, this is on page 204. I'm going to erase all this stuff, but believe me, we'll be using it. what I should do is give you a quiz. Name the first two most important equations in our course. Ta-da! I wonder if anybody would get 100 on that. Only if they listen to me. Now I'm on page 204 now. This is, we're talking about power and efficiency now. Page 204, power and, let's talk about power first. Well, now power, what power is it's work per time. It's work per time. And you've got an equation for work. We were just talking about it. It was F ds. And what we're going to do is we're going to divide that by a unit of time. And I think you could write that like this, F ds dt. Just scoot that dt up there in the integral. I think that's okay. The math, you could ask the math department if they would approve. Does anybody know what ds dt is? Oh, yeah, you know what that is. Ta-da, and you got f dv. And so if you're going from rest, from 0 to v, and just a minute now, I'm getting confused here. What I want to come up with is just f times v. I want to get rid of that integral somehow. And I'm getting confused. Just a minute here. I think I had a senior moment. Okay, let's see here. Totally organized as always. Okay, well, I can't find what I was looking for.
What problem are we on?
We're not doing a problem. We're talking about power right now. And
well, if you integrate that, don't you just get force times final velocity?
Well, that's what you're supposed to get. Yeah, that's what you're supposed to get. It's work per time. Yeah, all right. Here, now, let's see if we can do it this way. Now work is force times distance, right? We all know that. And so this could be an X or an S or whatever. And we're dividing by time. And by Jove, you get force times velocity. Now, if it's if they're not aligned and in the straight parallel with one another, then you need this dot product, and that's what you'll see in the book. But if they're in the same direction, it's just force times velocity. So we got our equation now for power. Then they have something called efficiency. Let's do that, and then we'll work a problem here. They use a Greek lowercase epsilon. That's one of their favorite. I don't know if you've noticed, but they use that epsilon all the time for all kinds of things, don't they? I think they use it in physics for different things. But what it is it's your output power divided by your input power. it turns out that like a motor, for instance, the output power is always a little less than your input power. Efficiency is always less than 100, or it's less than 1. It's less than 100%. Let's put it that way. Okay, now you know all about efficiency and power. Let's work a problem. Let me find us a problem that I can work. Yeah, this looks pretty good. This is F14.9. Shop around and find F14. There it is. Okay, we're going to work a problem now. I need the room, though. Sacrifice all this room, and we're going to do... Oh, I never wrote down your homework. Let me write that down. You have some homework. Assignment number 13. It's due Saturday. Today's Wednesday, right? This is due Saturday, and it's F14.2 on page 194 and 14.1 on page 195. And they're due Saturday. But you didn't need to know. I didn't need to write that. It's on Blackboard. You could look it up. But it's always nice to know. We're going to do F14.9 together. Here we go. Now let me draw the situation. You have a 100-pound. You have a 100-pound body. Yeah. There's a pulley. And this goes down here to this motor. There's a motor down here. And let me read this. Well, I could label this. This is A, B. No, they label that C, B, D. And they label the motor M. They put a little E right there for some reason. Now they said that the motor is winds the cable at constant speed of 3 feet per second. Tell you what you do. Take a little splotch of paint, and I put some red paint on that cable right there. And that splotch of paint is moving 3 feet per second into the motor. That's what they said. Constant speed, 3 feet per second. It's winding up, and the motor is pulling down on that. And the load weighs 100 pounds. And you have constant speed. Well, if you have constant speed, what will be the acceleration? What will be the acceleration if the speed is constant? What do you guys think? So somebody tell me. Go ahead.
Be 0.
It's 0. There's going to be no acceleration. Do I need to explain that? I guess not. I guess you understand if you have constant speed, you don't have any acceleration. So, you know what that means? That means that the sum of the forces is zero. Because Newton says the sum of the forces is equal to ma. Well, if a is zero, then the sum of the forces is zero. So here, look here. If this has 100 pounds going down, because that's how much they said it weighs, guess how much the tension in this cable is? It's 100 pounds. Guess how much the tension is in this cable? It's 100 pounds. Guess how much tension is in this cable? Well, it's 100 pounds. Now, how much tension do you have in this cable? Well, it'll be 200 pounds. Do I need to explain how come this cable has 200 pounds of tension in it? I guess you're okay. All right. Well, if you're okay, we're going to do the power of the motor. Now, this is going to be the output power of the motor. The output power of the motor is equal to the force times the velocity. And the motor's pulling on that with 200 pounds. And the velocity is 3 feet per second. So I'm getting 600 foot-pounds per second. That's the output power. Now, if you read the problem, they said the efficiency is 0.8. What that means is the output power divided by the input power is 0.8. But see, we know the output power, so you can solve for the input power. The input power, I'm going to shut up for 15 seconds. I want somebody out there, I'll call on somebody. I want somebody out there to find the input power. And I'm going to call on my friend William. William, unmute and say hello. Unmute
Hello.
and hello. William, solve this and tell us what the input power is.
That'd be 750.
Hey, that's what I got. Good going. We got 750 foot-pounds per second. Now, a lot of times they want motors in horsepower. Like I used to have a Briggs & Stratton lawnmower that was 3 horsepower. We got to figure out how much horsepower this one is. Well, here's how it works. Let me make a little room here. You're just going to have to memorize this. I'm sure it's in the book someplace. But 1 horsepower is equal to 550 foot-pounds per second. Now we got 750 foot-pounds per second. So divide that 750 by 550. And what we got for our input power, see there's a plug here. And you're going to have to go plug that into the PSO provides power here in Tulsa. And the input power that you're going to have to pay for when you get your electric bill I'm getting 1.36 horsepower. You're going to have to pay for that. Okay, let's see what we got for our answer. F14.9, go to the back and look up F14.9. And they say 1.36 horsepower. That's what they say. The book says that. Yay, we did great. Do you understand that problem? Well, let's work a let me talk to you now about just a minute here. Let me think. Let's just do another problem. Then we'll eventually talk about conservation of energy. We've talked about the work energy theorem, a little bit about power and efficiency. We're going to get to that. But let's work another problem. Let me, unless you have a question, I'm going to erase all this. Okay. Now, this problem that I want to do right now is 1438. It's 1438. You've got a kind of a ski slope type deal here. You've got a ski slope, and there's a skier here. Starts off at A. Here, I'll draw the skier. There you go. Here comes the skier down the slope. And they say there's no friction. Pretty slick. And when he gets to B, they want to know how fast he's going. Right now, he's going 5 meters a second. And then when he gets to B, they want us to find the velocity and the normal force. We can do that. Now, they said that he's at 15 meters right here. And the equation of this slope is 0.025 plus 5. Okay, well, let's solve for this distance x. See, this is your x-axis, and this is your y-axis, and they're telling us that y is 15. So we're going to take a moment and solve for x, and I'll shut up. You have time to do that. So, find the value of x. Go ahead. I know you can do it. I've got my value of x. Let me ask one of my excellent students here. Let's see. How about Stuart? Stuart, unmute, Stuart, and say hi.
Hello.
Yeah. Love that music in the background, Stuart. What'd you get for x, Stuart?
I got 20 meters.
What I got? See, this distance from here to here is 20 meters. The distance from here to here is 15 meters. Now, what do they want us to do? Let me read this again. If you just tuned in, we're doing problem 1438. It's on page 203. Stuart, since I got you on the line here, I want to know what this value of y is here. When x is 0, Stuart, what's y? You tell me.
5.
Yeah, good going. This little tiny distance here is 5. Excellent. Okay, now what do they want to know? They want to know how fast he's going when he gets down there. Well, there's a hard way and an easy way to do this. Why don't we do it both ways? That'd be fun. I lost my red pencil. Just a minute, guys. Oh, there it is. We'll do it the hard way first. See the forces on him. He's got a force of now what's his weight again? Did they tell us? 60 kilogram. He's a 60 kilogram. How much is that anyway? 60 kilograms. Yeah, it's only 132 pounds. I weigh more than that. But he's got a weight of, well, you have to do that in newtons though. Just a minute, let me get my newtons here. 60 times 9.81. I'm getting 588.6. I need red here. I'm doing my forces on the guy. I've got 588.6 newtons. Let me write it down here. 588.6 newtons. But he also has a normal force. See, there's a normal force doing that. That's it. There's no friction, they said. So there's only those two forces. That's it. Hey, let's do this the easy way. Then I'll do it the hard way. We're trying to find the velocity when he gets down here. Now, right here, he's going 5 meters a second. But he'll be going faster down here. And the way we're going to do it is with this work energy theorem thing. See, the normal doesn't do any work. Only the weight does work. Because, see, the normal is at a 90-degree angle. And remember, work is a dot product. And what that's equal to is F ds cosine of theta. And if theta is 90, see, the normal is 90 degrees from the path. Cosine of 90 is 0. Normal doesn't do any work. Only the 588.6 newtons does any work. And to find that work, you just take that 588.6 times, in this case, 10 meters, because, see, here's 15 meters. From here to here is 10 meters. So the total work done on the body is 588.6 newtons times 10 meters. I can do that in my head. 5,886 joules. And that's done by gravity. See, the normal doesn't do any work and there's no friction. And what's that equal to? Well, it's equal to 1/2 m, and m is what, 60 times v squared minus 1/2 m times 5 squared. Didn't they say it's going 5? Yeah. Okay, now here's an equation, guys. Ta-da, here you go. There's an equation with only one unknown. I'm going to shut up for a minute. I want you to solve for the velocity. You can do this. Go for it. I wonder if I did that right. Well, let me call on somebody here. Let's see. We've got Shane. Shane, unmute and say hello, please.
Hey.
Hey. Shane, have you solved this and gotten the velocity when it gets to right here at point B?
I got 14.87
That's what I
meters per
got.
second.
That's what I got. We can call it V2. It's 14.87 meters a second. See, he was going 5 meters a second, but down here, right here, he's going 14.87. Now that was the easy way. Now that was using the work energy theorem. Now the hard way, we could do this the hard way. Wonder if I got any room to do it on. Let's see here. Yeah, we'll make some room. Here we go. See, in general, your acceleration your force, your tangential component of your force is equal to your mass times gravity times times the, if that's an angle theta, times the sine of theta, and that's equal to ma tangential. I'm trying to find the velocity the hard way. I think that's right. The tangential component of the force is equal to mg sine theta. Yeah, it's equal to mat. So at is equal to g sine theta. Guys, we've already figured out the velocity the easy way, but we use this work energy theorem, but I'm showing you how to do it the hard way. Now we have an equation that goes like this. And you can integrate that. You can integrate that And what you'll get is the integral of oh gee, how are we going to get that d theta? Guys, never mind doing it the hard way. I don't want to do it the hard way. Forget it. We've got our velocity. We did it the easy way. I don't want to do it the hard way. We've answered part of the problem. Let's see if we got that part right. Look at 1438 with me, and let's see if we got that right. 1438. They said 14.9. What do we do with our answer? I think I erased it. Erased it? That's not. I erased it. I didn't erase it. I erased it. We have our velocity. It's 14.87. One of my excellent students just told me that. And the book says 14.9. So I'm pretty happy so far. Okay. They want to know what this normal force is. Well, to do that, what we're going to do is we're going to take the sum of the forces in the normal direction. Now, what we have there, man, I never put the normal direction on there. You're supposed to put red stuff and green stuff. Haven't I given you wonderful mini lectures on that over and over again? And I forgot to do it. Well, we're going to do it. The way you do these problems is you draw the problem. You put the red stuff on. That's the forces. Then you put the green stuff on. Now, what I'm talking about is the tangential and the normal unit vectors. You really need those in order to get the components correctly. Okay, I'm going to shut up. I'll give you 45 seconds. You probably are drawing this on your notes. I know you're taking excellent notes. Put them on there. Put the tangential and normal unit vectors on your sketch there. And then I'm going to do it on mine, and we'll see if they're the same. Go ahead. At the body, at the skier. See, yeah, there's a skier guy there, 60-pound guy. Gal, whatever, boy. 137 pounds. Might be a teenager, you know. Right now, if you just tuned in, we're drawing the tangential and normal unit vectors at this skier on problem 1438. And I'm going to go to my friend Shane. Shane, unmute and say hi, please.
Hey.
Hey. Hey, Shane, where do I put these green things?
I got the tangential vector pointing in the direction of motion.
Yeah, that's it. Good going, Shane. Let me put that in there. There's your tangential unit vector. Where's the other one?
Perpendicular to that.
Yeah.
Pointing up.
Yeah. Shane's got it. By Jove. Shane has got it. That's the normal unit vector. It always points to the inside of your curve. Okay, now we're ready. Now that we've done that, which you're supposed to do, now we're going to write our Newton's second law equation. Okay, well, let's see. In the normal direction, we have the normal. See, it's in that direction. That red arrow is in the same direction as that green arrow. Ah, but you have to subtract the 58 588.6 newtons cosine of theta. Cosine of theta. Man, do we know what theta is? We're going to have to figure out what this theta is. Anyway, all of that is going to equal a mass, 60 kilograms, times v squared over rho. Well, we got some work to do to get this. We do know the v, though. We got the v. Look here. We got the v. We figured it out. But we don't have the rho, and we don't have the theta. But we can get it. And here's how. I bet you remember this. The tangent of that theta is the same. That's the same theta as this theta here. They're both the same, and it's equal to dy dx. They teach you this in calculus. If you've taken calculus, I know that they told you that this is the slope. It's the rise over the run, and that's equal to the tangent of that angle theta. And if you do this, you'll come out with 0.05x. That's the first derivative with respect to x of this equation. And if x is 20, 0.05 times 20. I can almost do that in my head. I think it's 0.1, but I'm not sure. 0.05 times 20. Yeah, no, it's 1, isn't it? Let me do that again. 0.05 times 20. No, it's just plain old 1. According to that, theta must be 45 degrees. Does that kind of look like 45 degrees to you guys? Does this look like 45 degrees? Kind of. I bet you we did that right. Okay. Good going. All right. So what? Now I got lost. I had a senior moment. Does anybody know what I'm supposed to do now? Oh, plug that in here. Look here. If theta is 45 degrees, why can't we just stick it in there? That'd be okay. But we got to figure out what this rho thing is. All right, let's do that now. I need some room. I wonder if I can use this down here. And we have a lovely equation for this radius. What do they call it? The radius of curvature, that's it. It goes like this. But now wait a minute. Now I'm getting confused. They don't want it here. They want it here. Well, the theta there is 0, you know it? I don't know why I figured that theta up there, but there is no theta down there, it's 0. Never mind that. And what is the cosine of 0? Does anybody know? Cosine of 0?
1.
It's just 1. That's just a 1. Hey, guys, we're not up here. We're down here. I got mixed up. I need the radius of curvature down here. And here's the equation. Uh-oh, I need the second derivative. Well, I can get it. The second derivative That'd just be 0.05, wouldn't it? Can you see that? 0.05. dy dx is 0. The theta is 0 down there. It's just flat. So you just have 1 over 0.05. Is that 20? I did that in my head. That's dangerous. See, 1 divided by 0.05. Yeah, it's 20. Guys, we just figured out this radius of curvature is 20. And this here, I was doing it the wrong place. If you're down here, let me draw those red vectors. What did I do with my red? Oh, gee, I've lost my red pen again. Okay, now just a second here. There it is. When you're down here, you've got a normal force like this and a weight like this. The weight is 588.6 newtons. And I don't know the normal force, but we're going to know it in a minute, because the normal minus the weight will equal 60 v squared over 20, and we got the v. Down there, it's 14.87. Okay, we're going to solve this now. We are going to solve this equation, and we're going to get our normal force. Go ahead. I'll shut up and let you guys do that, and then we'll check it. Gee, I get a humongous number. I better do that again. Yeah, it's a big number. Let me go to one of my excellent students here and see what they got. Ryan, unmute and say hi, please, Ryan.
Hello.
Ryan, what did you get for this normal force?
I got 1,255 newtons.
That's what I got. That's what I got. I wonder if that's right. We'll look at the answer book here in a minute. Now, when I did it, I got 1,252 newtons. Well, let's don't fight over that 5 newtons. Go to the back and let's look up the answer for 1438 and see what it says. 1438, they say 1.25 kilonewtons. The book says 1.25 kilonewtons. And that's the same thing as what we got, Ryan. We did great. So that was a lot of fun. Now we could even find the normal force here. Wouldn't that be fun? We could. You would have to find the radius of curvature there, though. And you would have to, I would say you'd have to find the velocity, but that's given. They said it was 5 meters a second. They gave us that. And we found the angle, it's 45 degrees. We could find, that would be kind of fun to do that. All those that want to do that, that want to find the radius of curvature and the normal here at where the body is at 15 meters high, all those in favor say aye. Well, I didn't hear any ayes, so we won't do it. Nobody wants to do it. That's okay. We'll do something else. But that would be fun. I bet we could, though. I think we're equipped. We could find the normal force anywhere on this path, any place. If we can find it there, we could find it there or anyplace else. Okay, but we're not going to do that. We'll do something else. I need to talk to you about conservation. So let me find that in the book and we'll talk about that. Trying to find where they tell us. There we go. Conservative forces, potential energy, conservation of energy. Yeah, it's all in here. Okay, that's the topic. But I want to start on page 215. I'm going to erase all this unless somebody has something to say. I'm going to erase it. Here's your chance. Okay. We're going to move on now. Talk about conservation. Hey, you see that equation right there? That's the second most important equation in our class. It's very powerful. But what we're going to talk about right now is potential energy. Now, there's an equation on page 215. They do not emphasize this equation, but I think it's very important. I think it's the definition of potential energy. And what it says is the work done by it's got to be a special kind of force called a conservative force, is equal to the change in potential energy. Only they've written it in disguise. The way they write it is like this. It's really a definition. This is their secret symbol for work. This is the initial potential energy. That's the final. So you know what that is? It's the negative of the change in potential energy. Only I don't like their symbol. I much prefer PE for potential energy. And I much prefer W for work. But this equation, it's a definition, but it only works for what they call conservative forces. Now, conservative forces are those that the work done depends only on their position. Like, say, for instance, if you have a body here on the ground, and say it's a 50-pound body, and you lift it up 10 feet. Well, to do that, you're going to have to do 500 foot-pounds of work. That's what you do. But see, gravity does a negative 500 foot-pounds of work. That's the work done by gravity. Because, see, the whole time that this thing is going up here, gravity has got a force going down, but you're moving up, so that's negative work. And this work done by gravity is equal to the negative of the change in potential energy. So you guys took algebra, you know what the change in potential energy is. It's a positive 500 foot-pounds. If you lift a box up here 10 feet that weighs 50 pounds, it has increased its potential energy. It has now got 500 foot-pounds of gravitational potential energy. Now there's there's only two kinds of potential energy in this book that we study in dynamics. There's gravitational potential energy, and there's elastic potential energy. Now, there are other kinds. There's things dealing with the nucleus of atoms that we don't need to talk about. There's surface tension. There's magnetic. There's energy in magnetic fields. But the only two kinds of potential energy dealt with in this book are elastic and gravitational. And the equation is pretty easy. It's mgh and 1/2 kx squared for elastic. That's like springs, like rubber bands and springs. Okay, I think this is a very important equation. I prefer to write it like this, but it is in your book on page 215. They write it like this. It's the definition of the change in potential energy. Wait a minute, I did it wrong. This has got a negative sign right here. There, that's good. Now it's correct. I did it right here. Yeah. You can write it like this if you want. You can write it like this if you want. Now that we know that, let me show you the conservation of mechanical energy. Now this is on page 217, and then we'll work another. We have time for maybe one more problem. There's a little room right here, and we don't need their goofy definition there with their crazy secret codes there. Going back to the second most important equation in the course, if you add up all the works done on a body, it's equal to the change in kinetic energy. What that means is the final minus the initial kinetic energy. Now, if work is equal to the negative of the change in potential energy, let's say you have gravity acting. Well, then you're going to have work. The work done by gravity is the negative of the change in potential energy of gravity. You might have two bodies. You might have pulleys with two bodies. So if you had two bodies, you'd have to deal with the gravitational change in potential energy of two bodies. Theoretically, you could have elastic forces also. You could have springs involved. But never mind, you're going to have an equation like this. Now, when you write this, you know what that is. That's final minus initial. But with a negative sign in front of it, that's going to be the initial minus the final. And see that negative sign in front of it? See, this is the final minus initial, but with a negative sign in front of it, it's the initial minus the final. And you can keep on going if you have a bunch of connected bodies, and you're going to have this here. Bear with me, I'm going to show you a nice equation here in just a minute. What we're going to do is we're going to put all the initials together, And what you've got is the sum of all the initial potential energies minus, well, no, let's put it on the right. You see this kinetic energy right here? It's negative. Let's put it over here. But now keep in mind, if you have more than one body, you're going to have to deal with summations on all of these. So we'll put summations. So this will be the sum of all the initial kinetic energies. There's your equal sign. Now we're going to put all the sum of all the final potential energies. And look, you've got the sum of all the final kinetic energies. And we're done. Ta-da! We've got the sum of all the potential, the initial potential energies, the initial kinetic energies is equal to the sum of all the final potential energies plus all the final kinetic energies. They have a name for this. This equation is called the conservation Now, the way in this book, they call it the conservation of energy. What they should say is the conservation of mechanical energy. Because there are other kinds of energy like heat transfer, for instance. It's not mentioned in here. There's nothing in here about the energy of how hot something is. There is an equation where that is included. It's called the first law of thermodynamics. Those of you that take thermodynamics will learn that. And that's a more complete energy conservation law. But here we're not talking about any kind of temperature effects. We're just talking about things like springs, masses that are going up and down and have gravitational potential energy. But if you wondered where this came from, this conservation of energy equation, it came from here. It came from here, the work energy theorem. And it came from the definition of what the change in potential energy is. Now, there's a warning that goes with this. All of these works done must be done by conservative forces. And there's only two in this class. These have to be done by gravity, you put a little G there, or by a spring. You can have several works done by gravity because you might have several bodies. You can have several springs. But you can't have any outside forces. If there's another outside force, like for instance, friction, if you have friction, all bets are off. This equation doesn't work. So what I do in my class is I put a skull and crossbones right here. This is a nice equation, but if there's any other outside forces, even if there's a Mr. Griffin with a rope tugging on something, I'm not gravity and I'm not a spring. And so I don't qualify to go into this equation at all. If there's a work done by Mr. Griffin in here, you can still use this. You see this equation here? It's still good. It's still good. We can put a happy face on it. But this equation here, if there's an outside force, like if Mr. Griffin's yanking on your body with a rope there, it's no good. That's where the skull and crossbones comes in. Only if the forces are conservative. Okay, we got time for one last problem. Is there any question? Any question at all? I'm listening. I don't know if that made a lick of sense, but we tried. Okay, well, let's try this one here. We don't have much time is the sad thing. We have time maybe for this one last problem. Oh, it's hard to choose. These problems are all so wonderful. It's so difficult to choose. Well, okay. I think we got time maybe to do this one. We'll see. I'm going to make some room here. Kind of got a lot of theory today, didn't we? Now, this is problem F1415. And we might have time to do it. It's a collar with a spring attached to it. And the collar is moving 4 meters a second. Now, I think what they had in mind was to have a no friction. I think I erased the wrong lines there. Yeah, there we go. There's this collar there. It's a 2 kilogram collar. And this distance is 2 meters. The spring has a constant of 30 newtons per meter. It has an unstretched length of 1 meter. They want to know the velocity when this thing goes down 1 meter. Well, if that's 2 meters, 1 meter is about here. And so the spring, here I'll put it in green maybe. Let me write that K up here. K is 30 newtons per meter. See, when this thing is down here, we'll kind of do it in green. When it's down here, it's stretched out more. You get it? Yeah. And I tell you what that length is. It's the square root of 1 squared plus 2 squared. Well, I can do that. That's the square root of 5. You know what? Square root of 5 is 2.236 meters. Okay. They want to know the velocity when it gets there. Now, they didn't say anything about it being frictionless, but we're going to assume it is. It's in this section on conservation of energy, and if there is any friction, you can't use it. It's got a skull and crossbones on the equation. But I think we can use it here. And here's how the equation goes. the sum of all the potential energies initial, sum of all the kinetic energies initial, equal the sum of all the potential energies final, the sum of all the kinetic energies final. They call that the conservation of energy in this book. If there's any friction, you can't use it, but we'll assume that it's real slick. They put some drops of oil on there. And the initial, there's gravitational potential energy, and we'll say that that's equal to mgh. 2 kilograms, let me write it over here. I might run out of space here. 2 kilograms, 9.81 meters a second squared, 1 meter. That's the initial gravitational potential energy. Now the final gravitational potential energy is going to be 0. Because when it gets down to here, it's lost all of that. Okay, but there's another kind of potential energy, and that's the elastic potential energy. And see, that's equal to 1/2 K, which is 30, times the distance squared. But now the distance squared is 1 point. No, it's just 1. It's 1 meter squared. Because see, they said that this spring is unstretched at 1 meter. Well, it's stretched 2 meters. And in your equation 1/2 kx squared, this is how much the spring is stretched. If you have a spring that's 1 meter long and you stretch it 2 meters, well, then it's stretched 1 meter. And this is equal to, I can do that in my head. I think it's 15 joules, isn't it? Did I do that right? Yeah, okay. So now that's to start with. That has to go here. Plus 15 joules. Now the kinetic energy is 0. Didn't it start from, no, it didn't start from rest. It's going 4 meters a second. So it's 1/2 the mass times 4 squared. Okay, now over here we have, when it gets down here, it has 0 gravitational. But what is the elastic? The elastic potential energy is, oh gee, I have about 1 minute to do this. It's 1/2 30 times 1.136 squared. See, that's how much it's stretched when it gets to there. Let me see what that is.
Isn't that 1.236 meters?
Oh, there's a honking thank you point for that fine student. It's 1.236. Good going. We were going to get the wrong answer. Let's see, that's 15 times 1.236 squared. If I did that right, I'm getting 22.9154 joules. Let me put that in there. Plus the final kinetic energies, which is 1/2 2 times v squared. Hey, look at here. Here's an equation with only one unknown. These are all the initial values of energies: gravitational, elastic, kinetic. These are all the final energies: gravitational, elastic, kinetic. Okay, you solve that. I'm going to look up the answer in the back and we'll see if we get it. Go for it. Hurry though, because we're out of time. It's sad. This is 1415. But they have these fundamental problems solved for you in the back. If we did it wrong, you can read it. Well, I bet we did it right. F1415. They're getting an answer in the back of the book of 5.26 meters a second. I wonder if that's what you get when you do this. I'm going to do it real quick. Boy, Jove, that's exactly what I get. Well, what I get is 5.264, and the answer book says 5.26. So we use the conservation of mechanical energy. And you got some homework to do. Go and do your homework. Any last comments from anybody? Here's your chance. Okay, well, I'm going to say goodbye for now, and we'll see you Monday at 9:30, right? Yeah. See you then. Bye-bye.